Swayam Prabha. Digital India. Educated India.
Welcome everyone. So, we were in the previous lecture, we were talking about penalty methods. Penalty methods are a way of converting a constrained optimization problem into an unconstrained one by penalizing the constraint. So, we introduced this additional function called the penalty function. The penalty function was supposed to have required to have the property that it would be continuous, it would be non-negative, and it would be 0 entirely on the feasible region of the problem. So, it would be 0 everywhere on the feasible region of the problem, and outside the feasible region it would be strictly positive, right. So, and using this penalty method penalty function, we recast a constrained optimization problem as an unconstrained optimization problem by removing the constraints and adding to the objective a penalty parameter times the penalty function. So, the new objective was the original objective plus a penalty parameter times the penalty function. Now, one of the things we found there was that as the limit, if you computed the sequence of unconstrained minimizations by letting the penalty parameter go to infinity, one of the things we found there was that this sequence if it converges, that means any limit point of this sequence converge to the global minimum of the constrained optimization problem. Now, this is a extremely powerful technique because it allows us a way of essentially reducing any constrained optimization to simply an unconstrained one. However, there are a few little drawbacks which I will just discuss. One of the things that we find in the penalty in this sort of method is that that one converges rather slowly to a feasible point, meaning that the feasible in order to become actually feasible, your penalty parameter needs to be extremely large, right. So, let us see one kind of penalty method in which we are using what is called a norm penalty or a quadratic penalty. Okay. So, consider this optimization problem. Suppose we are minimizing this function f x subject to the constraint h of x equal to 0. Now, one possible choice for the penalty function for this sort of problem, since this is a equality constraint, one possible choice for a penalty function is to simply penalize h by the penalty function p of x can be taken as simply norm of h of x the whole square. Okay. And then we can consider the objective, which is f x plus plus c times norm h of x whole square. And the idea is that we let c increase to infinity, and then we compute at each iteration we minimize this particular problem, right. Now, where is the catch here? So, the catch is the following. So, let me mention this theorem. So, the theorem is the following. So, let x star be a limit point let x star be a limit point of this sequence xk. So, let me say for example, let us take c as c equal to ck and ck goes to infinity, right. Let x star be the limit point of the sequence xk obtained by minimizing f of x plus ck norm h of x the whole squared, all right, and obtained by minimizing f of x plus ck norm h of x the whole squared, where ck is tending to infinity, is increasing to infinity, all right. Okay. Now, then if x star is infeasible, then it is a stationary point of norm of h of x squared. So, if it is infeasible, it actually ends up as a stationary point of norm of h of x squared. So, you end up actually minimizing not f, but or not f plus this, but rather eventually ending up minimizing this. So, you end up at a stationary point of this. Okay. On the other hand, if x star is feasible, and the gradients of the constraints. So, here by I did not mention this, but these are basically, this could be even a vector of constraints. So, we will allow for this. So, let us say, let us write this as a j equal to 0, j equals 1 to p, say, and then we could write this as norm of this. Okay. So, this would be the penalty function for the kth constraint, and this would be then a summation from 1 to p. Okay. All right. So, I will just adjust this to allow for a vector, and the constraint gradients the constraint gradients are these, are linearly independent then x star is a KKT point. Of the constraint problem. the constraint optimization problem. For such points, we have that for any sequence k such that the limit as k in k x k tends to x star, we have limit k in k c k times h j of x k equals we have that the limit as k of k as k runs over the sequence capital K, the limit of c k times h j of x k equals theta j, where theta j is the Lagrange multiplier corresponding to the constraint h j of x equal to 0 in the KKT conditions. At point x star. So, what does this mean? What this statement effectively is saying is that if you take the sequence of x k's that are obtained by solving the penalized problem and you let this you look at any limit point x star of this sequence, then you have two possibilities. One is that the limit point is actually infeasible for the original problem, in which case it turns out that the limit point is actually a stationary point. In which case it turns out that the limit point is actually a stationary point of your penalty function. So, you end up actually at a stationary point of the penalty function, and that may have no relation whatsoever to the to any solution of the original problem. On the other hand, if you are feasible, then it turns out that if your constraint gradients are linearly independent, say for instance, if LICQ holds, and then you actually end up at a KKT point of the constraint optimization problem. Moreover, with this penalty function, moreover you have this additional property that Ck times Hj of xk tends to approaches the Lagrange multiplier. Ck times Hj of xk approaches the Lagrange multiplier. Now, this is a particular property of this quadratic penalty that we are considering. So, this limiting value becomes the value of the Lagrange ends up at the optimal value of the Lagrange multiplier at for which for the KKT conditions at point at point x star. All right. So, this is true for each equality constraint. Okay. So, this is for all, this is holds for all p, for all j going from 1 to p, all the p equality constraints. Now, what does this mean? This means that effectively for k large, this basically is saying that for k large, your Ck times Hj of xk is not becoming 0, but rather coming close to a constant equal to the Lagrange multiplier, right. So, which means that if I just think of Hj of xk itself, Hj of xk starts approaching a constant divided by Ck. Now, this particular this particular thing is a somewhat undesirable, because what it effectively means is that Hk is never actually going to become exactly equal to 0, which is what you would need. Hj has to be exactly equal to 0 for you to have feasibility. So, you are never actually going to have Hj exactly equal to 0 unless Ck itself becomes infinite, right. So, unless Ck becomes infinite, this is not going to work out exactly, right. So, which means that you really need Ck to blow up to infinity, and so for if you terminate the algorithm at any finite iteration, although in the limit you would end up at a solution, but if you terminate the algorithm at any finite iteration, you may not actually be feasible. In fact, you would in general not be feasible. You will be feasibility will be off by a certain amount. Now, there are two ways of remedying this, and I will talk about one particular approach first, and then we will go to another approach. So, one particular approach is to change the penalty function itself. So, the reason this is happening is because your penalty function right now is actually quite smooth. The penalty function that we are using, it has increases, the quadratic penalty function tends to increase gradually. If you see this quadratic penalty function, effectively if you see how it looks, it essentially looks like a gradual increase towards infinity. That's the behavior of this function, right, t and p of t. The penalty function p of t, which is equal to t square. So, it is not quite doing a sharp penalization near the feasible region. So, as a result, your method tends to sort of become a little bit ambivalent about points that are close to, that are around here, that are close to the feasible region, but may be feasible or infeasible. So, it is not the penalty out here is not sharp enough. Now, one way of therefore dealing with this is to put in that sort of sharp penalty, and that is what I will talk about right now. So, a sharp penalty would effectively mean that you need to put in a penalty that goes from inside the feasible region to outside the feasible region in a very in a dramatic sort of way. So, that usually means that you would lose differentiability of the penalty function. You can have continuity, but the function will not be differentiable anymore. Just like the quadratic function smoothly increase, you cannot expect that sort of behavior. So, you are then looking for a penalty function that is not smooth, right. So, that is what is called a non-smooth penalty function. So, a non-smooth penalty function. So, one simple example of a non-smooth penalty function is the modulus function, so the absolute value function, right. So, if you have, so you take the absolute value, so p of h of x as simply, or hj of x as simply the absolute value of h of x instead of the square of this quantity. Now, this function unlike the one before, this is your quadratic function, quadratic penalty. The one where you are using the modulus or the absolute value, that function would look like this. Now, absolute value being less would eventually become will eventually, this being linear, it will eventually the not penalize as severely as the quadratic, because the quadratic would penalizes in a much more dramatic way for larger values. But for smaller values, the penalty in the absolute value, or the L1 penalty, this is also called the L1 penalty. So, for smaller values of t, the penalty here is going to be larger, because for smaller values mod x will actually be, smaller values of t, mod t will actually be or absolute value of t uh, would be less than t square, right. So, this is the thing that we want to end up exploiting. So, then what we are then looking for is, then we are the problem we are solving then is this problem q of x given c k, which is we are going to define this q of x given c k as f of x plus c k times summation absolute value of h j of x, as j ranges from 1 to p, and and at each step you minimize this q of this in order to get x k. Now, the theorem that we can get from this is the following. Suppose x star is a strict local minimum of the constrained optimization problem at which the KKT conditions are satisfied. With Lagrange multipliers with Lagrange multipliers theta j for j in 1, j going from 1 to p. Then x star is a local minimizer of q and c for all c greater than c star, where c star is equal to the maximum of the Lagrange multipliers maximum of these Lagrange multipliers. Okay. So, x star turns out to be is a local minimizer is a local minimizer of this for all of the, or for all c greater than c star. What does this mean? That if you found a, if you can find if you can set your penalty parameter to be larger than c star, where c star is simply the largest of the Lagrange multipliers that we have, then you can get the true solution. The solution of the constraint problem is also a minimum of the penalized problem, which means that it suffices to set the penalty parameter to be larger than C star, and that solves the problem. Right. So, this is actually very powerful, because it lets us effectively get to the solution of the constraint problem through an unconstrained problem and with a finite penalty parameter value, without having to deal with infinities anywhere. And so, this is but the only catch here is that the actual minimization of the penalty of this function, the penalized function, the one with the mod h here in the objective, mod h here, the actual minimization becomes a little problematic, because now you have a non-differentiable objective. The objective is f plus absolute value of h j of x, which is not necessarily a differentiable function. This becomes this becomes the catch, but this is the price you have to pay for getting a strong result of this kind. Right. So, this is one of the ways by which you can use a finite value of the penalty and yet use the penalty method to get to the solution of a constrained optimization problem.